Okay, in this video, I'm going to be proving the method BlackPenRedPen used. Say we have a function. F that takes in from all the values from 0, 1, 2, all the way up until n, and it'll output a real number. Okay? And here's a theorem. There exists a polynomial P from R to R such that P of K equals F of K for K equals 0, 1, all the way up until n. Okay, let's prove this theorem. Okay, so we're going to define a couple things with how BlackPenRedPen did it in his original video. Delta x sub 0, to the power of 0, but it's not really to the power, it's just the best notation I could come up with. Sub k is going to be equal to f of k. Okay, and then we define delta x of n plus 1 sub k is going to be equal to delta x of n k plus 1 minus delta x n k. Okay, that's it. This is just the nth difference, right? Because if I had my f of x, f of 0, f of 1, f of 2, I'm going to do it with 3. Then the difference here is f of 1 minus f of 2, or what I'm calling delta. So this is going to be right here, that's going to be delta x 0, 0, that's going to be delta x 1, 0, that's going to be delta x 2, 0. Okay, this right here is going to be delta x, delta f of 1 minus f of 0. That's going to be delta x 0, 1. So I changed the superscript on this. Right there, I'm going to get f of 2 minus f of 1, which is going to be delta x 1, 0. Then the difference between those two, delta x 1, 0 minus delta x 1, 1 minus delta x 0, 1 is going to be delta x 0, 2. Okay, that's how we define it. They're just the differences. And I'm going to prove a couple things about these differences and something about the n choose k function. So what's the thing I'm going to prove about the differences? Well, I'm going to prove that delta x sub k to the n plus delta x sub k to the n plus 1, what's this going to be? Well, let's put in the definition here. That's going to be delta x to the n k plus, that right there is going to be delta x sub k plus 1 to the n minus delta x sub k to the n, right? From the definition. Those cancel out, and we just get delta x to the n k plus 1. That's an important fact. Very important fact. Okay, and another important fact is about n choose k, is that n choose k is equal to n minus 1 choose k plus, I'll do k minus 1, plus n minus 1 choose k. So n minus 1 choose k minus 1 plus n minus 1 choose k. The proof of this is because if I have n times n minus 1 all the way up until n minus k plus 1 over k factorial, I'm going to do n plus 1 there, and then n there and n there. Okay, and then I add on that. So this right here is that one. Then I add on that n times all the way down until n minus k, which is that one. Is it n minus k plus 1? That's from the definition. Then it'll be n minus k minus 1 plus 1, which will be n minus k plus 2. There we go. Over k minus 1 factorial. So what I'll do is I'll multiply this by k, right? And then they have a common denominator. So I could get that n times n minus 1 all the way down until n minus k plus 1 plus n all the way down until n minus k plus 2 times k over k factorial. Right? I can factor out here n times n minus 1 all the way down until n minus k plus 2, but I can't factor out further than that. So I'm going to have n minus k plus 1 plus k, which is just n plus 1. Then all of that over k factorial. And as you can see, this is just n choose k, n plus 1 choose k. Okay, these are two very important facts for proving this. And from there, it'll be kind of simple, actually. And I'll put it... Okay, so I'll put equals delta x n k plus 1, and n choose k is going to be equal to n minus 1 choose k minus 1 plus n minus 1 choose k. These are my facts of the day. Okay, so now let's prove our theorem. Okay, let p of x equal, okay, I'm going to say delta x 0, 0 times n choose 0 times, I'll say p of n. Okay, so p of n is going to be delta x 0, 0 times n choose 0 plus delta x 0, 1 n choose 1 plus all the way up until delta x 0 n. I should call that a different thing. I'll call it d. So delta x 0 d, then n choose d. Okay, so then p of k, just the general k, is that you actually can ignore most of these, because if k is bigger on the denominator, then the choose function is going to be equal to 0. So p of k is equal to delta, and then for k an element 1 to n, or d, it's going to be delta x 0, 0, and k choose 0, plus delta x 1, 0. And what I'm going to do, I'm going to write this vertically, plus delta x 0, 1. And what I'm going to do is I'm going to write n choose 1 as k minus 1 choose 0 plus k minus 1 choose 1 by that fact. Okay? And then plus all the way down until I get plus delta x 0, k, because I only need to do it up to k because all the other ones are just going to be 0, times k, choose k. Okay, and I'm going to write k choose k as k minus 1, choose k minus 1. Okay, which, in fact, gives us, I'm going to rewrite k choose 0 as k minus 1 choose 0, because that's still going to be 1, and k choose k as k minus 1 choose k minus 1, because that's still 1. Okay, so then, from that, by factoring, I'm going to get k minus 1 choose 0 times delta x 0, 0 plus delta x 0, 1, plus, then I'm going to have, if you imagine, k minus 1 choose 1 times delta x 0, 1 plus delta x 0, 2. By bringing that one, I'll write the delta x 0, 2 times k minus 1 choose 0 plus k choose 1, k minus 1 choose 2, right? And so, right there, that factor of delta x 0, 2 goes there, and we combine them right here, plus, okay, plus, and then at the end of it, we get k minus 1, choose k minus 1, times, what do we get? Delta x 0 k minus 1 plus delta x 0 k. And by that fact right there, guess what this is? It's k minus 1, choose 0, times delta x 1. By that fact, 1, 0, plus, then we're going to have all the way up until k minus 1, choose k minus 1, and then delta x 0 k minus 1, or 1 k minus 1. Okay? Then you can imagine this would work for the ith term by replacing all those 1s with i's. You can prove this yourself. Replace all those 1s with i's. Okay, so replace all those 1 with i's. And what we can do is we can set I equals a k. So for I equals k, guess what we're going to get? K minus I is k minus k, which is 0. 0 choose 0. And then delta x, 0 on the top, and then k on the bottom. Definition, 0 choose 0 is 1. Delta x, 0k, is, by definition, f of k. 1 times f of k, that's f of k. F of k. And so what I proved is that this polynomial, p of k, is equal to f of k for k an element of 1, 2, 3, all the way up until d. And so what I just showed you is that BlackPenRedPen's ghetto way of doing this is in fact correct. And also, this took me way longer than it should have because it was actually kind of simple.